Hello everyone, in this paper we present simple and effective method by minimizing the adaptive consistency regularizer ACR for long-tail semi-supervised learning LTSSL with unknown class distributions of the unlabeled data. We implement our idea in a double branch network and realize ACR through the on-the-fly distribution estimation and novel dynamic logic adjustment. We empirically show that our method significantly outperforms all competing methods under various scenarios, offering a solid baseline for future studies in this task. Long-tail semi-supervised learning (LTSSL) has received tremendous attention recently. Existing LTSSL algorithms typically assume that class distributions of labeled and unlabeled data are almost identical. Those algorithms build upon the assumption that can severely suffer when the class distribution of labeled and unlabeled data are mismatched. So we propose a simple algorithm to effectively use unlabeled data through the adaptive consistency regularizer, which is built upon one of the most popular SSL algorithms, fixed match. Concretely, ACR is developed based on two findings. To learn a class balance classifier, it is helpful to generate pseudolabels bias appropriately towards the minority class, whereas to learn a better future extractor, the accuracy of pseudolabels is critical. Those two findings seem to be contradict. We thus present a two-branch network, including a balanced branch and a standard branch, to solve this conflict. Specifically, for standard branch, we import fixed match, which optimizes the standard cross entropy on labeled data to learn good future representations. For the balanced branch, we optimize the balance of max, which is an improved version of standard cross entropy. Pi y is an estimate of barrier for class y, which is approximated by empirical frequency of the training samples, and tau is a scaling parameter that affects the intensity of logic adjustment. Through minimizing balance of max, balanced branch can predict more balanced predictive probabilities. Inspiring by the first finding, we propose to apply post-hoc logic adjustment to the output of standard classifier F, whose predictions are initially biased towards majority classes. The refined logics are used to generate pseudolabels, which will be treated as targets for the balanced branch. For second finding, we empirically find that the standard branch can produce high quality of pseudolabels, and their overall distribution matches the true distribution in the consistent setting, but are biased towards majority classes in other two scenarios with different degrees. Fortunately, we overcome this difficulty by a simple dynamic logic adjustment in a unified formula according to the unlabeled data class distribution estimate, which help ACR automatically change the intensity of logic adjustment. To estimate the tree distribution, we first craft three anchor distributions, including the class distribution of a labeled data, a uniform distribution, and a reversed class distribution of the labeled data. Then we take the pseudolabels produced by the balanced branch to estimate the distribution and calculate its distance to each anchor distribution by bi-directional KR divergence. Based on the distances to anchor distributions, ACR can adaptively handle various class distributions of unlabeled data in a unified formula that adjusts the scaling parameter tau like this. In this formula, consistent and reverse settings will restore a small and large tau value respectively. You can see section 3.2 of our paper for a detailed explanation. Figures illustrate the bidirectional KR divergence for different unlabeled data. distributions and tau values during the training, which conforms to the description in our paper. In addition, we select unlabeled data samples with high predictive confidence and introduce another complementary term to further enhance the quality of pseudolabels. In this way, we can select more samples for the minority classes by considering the balance branches output, obtain more confident samples through the newly constructed sample mask, which is beneficial for consistency loss to work. We demonstrate this effect of new sample mask selection principle in our ablation studies. Here we show some results displayed in our paper. For consistent setting, ACR outperforms all algorithms, even though most of these methods are particularly developed based on the assumption that labeled and unlabeled data share the same class distribution. For inconsistent setting, without exception, ACR surpasses the previous methods by a large margin. Here we display the precision and recall of pseudolabels for DASO and ACR on CFR 10 LT dataset in uniform and reverse settings, which illustrates ACR produces the pseudolabels of high quality in both uniform and reverse settings. We can also conclude two key observations from confusion matrix. ACR achieves higher overall accuracy for classes, and ACR significantly improves the minority class accuracy. We also generalize ACR to more realistic LTSSL settings. The performance gain becomes increasingly significant as the class distribution of unlabeled data changes from consistent to reversed. This demonstrates the capability of our method to handle various realistic LTSSL problems adaptively. It can be seen from TSNE visualization that the representation obtained by ACR follows for clear class boundaries. Extensive ablation studies to tease apart the factors that are most important to ACR success. In conclusion, we present a simple and effective method by minimizing the adaptive consistency regularizer for long-tail semi-supervised learning with unknown class distribution of unlabeled data. My email address is here. Please feel free to send emails to me if you are interested in our work or have some questions about our paper. Thank you for your listening.